20 students in class. The first estimator is to basically take the first 2 students in class, record their height, and then basically take the average between them and use that as your estimate. Okay. The second estimate is to take the first person that comes to class, the 11th person that comes to class, and then the last person who comes to class. And you weight them a little differently, so that 11th person that comes to class, you weight them a little bit more than the first and the last person that comes to class. And then the third is what we typically use, which is the mean, right? So we could just take the mean, and so remember another way to write this is 1 over 20 times y1 plus 1 over 20 y2 plus 1 over 20 y20. Okay, so we have 20 individuals, and what are the implications for using these 3 estimates? So the first part says which of these estimators are unbiased estimators of mu. Okay, and so we know that an unbiased estimator is going to be equal to mu, right? So if mu hat is unbiased, it's going to be exactly equal to mu, okay? And so what we do for this first part, for part A, is take the expectation of each of them. And so I'll do, for the first one, here we're going to take the expectation of just taking the first 2 individuals. Okay, so we run this expectation operator through. Obviously, the 1/2 just moves right through. Remember, we have this, this rule where the expectation of A plus BX equals A plus B times the expectation of X, if X is a random variable. And so we can just pass it through 1/2, and then we have the expectation of Y1 plus the expectation of Y2. Which we know for all y, the expectation of any observation is just mu, the population mean. And so here, essentially a 1/2 times 2 mu or mu. Okay, so even though that first estimator might seem very silly, right? Why would you only use 2 observations when you have 20? It's still unbiased. So on average, there's no reason to think that our estimate for height would be off. And so you do the same for mu2, mu3. You should find that actually they're all unbiased. Okay, they're all unbiased. And if you went to an infinite number of classes and redid this over and over again, and then got a distribution of the different mu's, the estimates for each class, then the average of all those samples would be about equal to the mean. Right? So if you did it for, let's say, 100 classes, you went here, and you recorded your mu hat 1. So you took the first 2 people in class, took their height, and then you jetted over to down the hall, took the first 2 people, recorded their height, took the average, jetted off. And you do that for every class. You get a distribution of each of those averages. The average of the averages, right, should be about equal to mu. All right, so that's part A. Part B, so the other key here is that anytime you're asked whether something's unbiased or not, you're going to take an expectation. Okay, so you might look at this and you might not know what to do first. Anytime you see, if you're being asked whether an estimator is biased or unbiased, you need to take an expectation of the estimator. And to see that if the expectation of the estimator is equal to the true parameter value. Okay. So the second part then says rank the 3 estimators in terms of minimum variance. And actually, one thing I do remember about this test is a lot of test takers, looked at these and they said, well, this is the one we use. That one seems very silly. This one seems less silly. So minimum, next, and next, right? This has got the most variance because we don't do that. And that would be correct. But there's actually a way to calculate it, right? And so if we take this first way of estimating the variance of mu1 hat, again, we're taking the variance of 1/2 y1 plus y2. And so remember, when it comes to variance, you're taking the variance of a plus bx. That's equal to b squared times the variance of x. Right, so a disappears. But we have to square anything that runs through variance operator. And so that's what's going to happen to this 1/2. Right, this 1/2 is going to run through the variance operator, but it's going to be squared. Okay? And so we're going to end up with 1/4 times the variance of y1 plus the variance of y2. So obviously 1/4 times 2 sigma squared, so we get 1/2 sigma squared. Okay, 1/2 sigma squared. And so you can see right away if you compare this here, for this mu3, you're going to get 1/20 squared, times 20. Basically you're going to get 1/20 times sigma squared, right? Which is much lower, which is what we want. So we do that for each estimator, 2 and 3, and you'll find that it's basically what you would have in there. Does that make sense? Yes.
Sir, just I want to ask you about the tests, like in the review questions, like for example, when you have v1 plus v2 equals to -1.
Which one?
The review questions,
Yes.
2008.
Okay.
Yeah. If you have v1 plus v2 is equals to -1, what test would you use?
So the let me see what that is. Oh, I see. Okay, so part C. Okay, yeah. All right. All right, so for this one, we have 4 variables in there. And so for part C, the hypothesis is that beta 1 plus beta 2 equals -1. Beta 1 plus beta 2 equals -1. And so even though this includes 2 parameters, it's still just a single, it's a single value, right? Or it's a single hypothesis. So here we have a single hypothesis. So we're going to eventually do a t-test. So there are a couple different ways to do this test. I'm going to suggest what I think is the easiest, which is to say that we can reassign this phi value to be equal to beta 1 plus beta 2, right? And so our hypothesis then becomes, if we could find phi, that equals -1, right? So just like everything else, we just need to substitute this in. So we can subtract beta 2 from both sides. Okay. And so then we can substitute in for beta 1, this phi minus beta 2, x1 plus beta 2, x2, right, hold on. And then just like we did for the other one, we can